right, get a different color pen, and let's check over these. If you didn't quite finish, you'll still get the benefit of seeing the questions and working along through the last maybe one or two with me, okay? So big idea is, so far, like after looking through this PowerPoint, there's just a lot of molecular geometry, a lot of bond angles, the physical properties that come because of it being a polar or non-polar molecule, the comparison between like metallic, ionic, semiconductor, network covalence, and so forth. So it's a lot of that stuff we did in our last unit. So I'm going to hit this pretty quickly, but I do think that there's a lot of really easy points here. So I just want to make sure you're seeing it a second or third or fourth time at this point, okay? So we'll finish this in the next, we'll have some time to spare today in class so you guys can start on the last big idea. All right, so has 2 lone pairs, 4? Okay, so we know water has 2 lone pairs on the oxygen itself to give it octet. Hydrogen, does it achieve octet? Does it, yeah or nay? No, it achieves duet, right, which is the 2 valence electron rule. I'm just making sure you're clear on that because there's like really easy multiple choice questions where hydrogen's between things. No, hydrogen can't be on 2, like between things because it can have 4 valence electrons. 5, less than octet. C, so that's, why is boron tetrahydride able to achieve less than octet? Because why? Right, so it has 3 valence electrons, so then it bonds 3 times, and it actually is okay with 6 valence electrons. So what are the exceptions to octet one more time? Hydrogen's going to have 2. What about, go in order. Hydrogen's going to have 2 most of the time. What about beryllium? It's okay with 4 valence electrons in a molecule setting because it has 2 valence electrons, and so it bonds twice to give it a full, its own octet of 4. Boron would have 6, carbon would have octet, right? You guys with me? Okay, so carbon will have octet, and then everything past that will have octet or over octet, right? So when do we start hitting expanded octet? Phosphorus, right? Phosphorus, sulfur, chlorine, argon, and down. So basically they have access to D block electron orbitals, so they can pop extra electrons in there as needed. Okay, 6. All right, I heard both. I heard A and C. Loud and proud, people. C, because name the geometries, like the molecular geometries on each of these. What's the geometry of water? It's bent at an angle of what? So it's a variety, like it's a derivative of tetrahedral, right? Because it has 2 lone pairs and 2 ligands, making 4 electron domains overall. Normally tetrahedral is assigned a what bond angle? 109.5. But every time you take away a ligand and make it a lone pair, it squishes it, right? It repels, so it's going to decrease the bond angle. That goes to 107, and then a second time we'll go down to 104.5. But yet again, it's still, close to 109.5. That's going to be tetra electron group geometry, but trigonal pyramidal overall. What's the bond angle here? Well, it's the same derivative from water. So anytime you have 1, 2, 3, 4 electron domains in general, you're going to be 109.5, 104.5 to 109.5, really, because that's the small variation of repulsion occurring. So if you have tetrageometry in electron group geometry, you have to be between here. So not even close to 120. But C being, what's the geometry on C? Trigonal planar, right? Boron with 3 attachments, no lone pairs, is going to be 1, 2, 3. No, not a pyramidal structure, so it would be trigonal planar, and what would be the bond angle here? 120, so that's the largest. And then again, methane is what? Tetra, so about 109.5, and then same thing down here, 109.5. Okay, and you've drawn these guys enough. I'm hoping you don't have to continue to draw them, but absolutely if you have time to do. 7. B. All right, we were kind of gone over that. 42. Loud and proud. B as I was going to say boron, but B, right? So increasing boiling point. What made you choose, why is hydrochloric acid down here and hydrochloric acid's high? Oh, did I skip 7? No, I got 7. No, it's not B. I looked at 7. My bad. I was like, why is that? Okay, so, no, I was like, why did we choose that? You guys explain to me. No, yeah, definitely E, because why is this one at HF going to be the highest, the boiling point? The ability to hydrogen bond. Okay. 47, I think is what I was looking for. 47. Isomers. Okay, so that's just a different structure, same chemical formula. What is it? C. All right, so basically this is an ether, something with something on ether side, dimethyl ether, and this is an alcohol, but the same chemical formula applies the whole way through. 49. Louder. D as in dog. So you said, okay. Greatest solubility. So basically this question is about like dissolves like. This is nonpolar because it's just a straight chain alkane. This is nonpolar. The rest of them are polar or ionic, so it's not going to dissolve in nonpolars. 54. D, good. Ionic solid, whenever you are forming strong ion dipoles, it's very stable, very good for ionization or for solubility process. And then increase in entropy upon dissolving. That means that upon making more. This was a question. Hold on, I'm going to go back to this in a second. But this was a question that I think I have to go back and check my key because I was making an answer key to another exam this weekend, and I think I marked it wrong on your last exam. Does anybody remember a question similar to this, but it was in pictorial form? Remember, it was like I need to go back and just basically add that point. So my assumption made a whole lot of sense to me, but now it makes more sense to think about it this way. If you have water, I'm just going to draw these bubbles of water, and that's water and water, and you have a salt crystal. Whenever you break the IMFs of water, like, hydrogen bonding, you overcome this so that the salt can mix with it. Is that increasing or decreasing entropy? Right, so you're taking a really organized water blob and you're basically breaking it up. So that delta S should be positive because you're increasing the disorder. If you do the same thing and you break up the ionic solid, delta S should be what? Positive. Okay, so what the question, what was the question? It was the one you had like you had delta H and delta S for each individual step of the solution process. But they said as you put water and ion together in a mixed fashion, how did we answer this? Delta S should what? I said it should be positive because my analogy was like if I took green M&Ms and brown M&Ms and mixed them together, two different things coming together making a greater amount of disorder. So I said a positive delta S, but I'm pretty sure on the answer key, I might have to double check this in a second, they said a negative delta S because of the nature of how stability is creating more stable interactions, so they're actually lowering energy, so it's related to the energy debate, not the mixing debate. So this is what I believe they said was negative because upon the ion dipoles forming, it's more stable, lower energy, less disorder. Does that make sense? But then what do they say over here? Increase in entropy upon dissolving. That's what most people would think. So I will show you guys that question, but it was on your last test. All right, let's finish this. 71. A, good. So you're looking at just basically drawing structures and counting singles and double bonds. And then 30 or 73. Who just knows that? Some of us just know it because we've drawn those in twice or 3 times in our life, and we know that you have the ability to draw it like this. How many electrons are in ozone? How much? 18, 6, 6, 6, right? 18. So we can draw this way or double one on the other side. And this is a question they've asked twice in 2 years. So I don't know if they'll ask it again. But people had to draw either ozone or a carbonate or a bicarbonate or something that had resonance on the Fourier response. And basically, if you didn't have it right, you just didn't get points. But it's easy enough to get this. Just imagine though, there's a bracket and an arrow between these. Okay, so just put it in as many locations as it would be possible. Yeah. There are stronger intermolecular forces of attraction between A and B versus whatever it is you're not comparing, or you're comparing but saying it's less soluble. It's more about the IMFs. Okay. All right. So I'd like for you guys to do the FRQs in partners today, only because I want you to try to explain, like literally, whatever's off the top of your head, you must say. Okay. So write down write down what you need to so we can check them, but go ahead and go up to 2013, okay? You have to sit with a partner and talk, okay? I want you to be able to verbalize some of this. I'll finish giving you the other color. So sit next to somebody, talk it out, let's go. 2013. Try to justify or win them over if you think you're right and you're not. Don't tell them wrong information. Hey Megan, bring me that paper when you're done. I like that you guys mixed it up a lot, you know? You can say, I don't think so, in like some sort of sassy remark on the AP exam. Are you crazy? No, this is false. Oh, teeny tiny. Load this up. Draw that. Alright, we are going to check these now. Alright, finish the part you were writing, and then we are going to check these. Alright, and you're getting a colorful device to write with in 10, 9, 8, 7, 6. This is the first one you guys had. 5, 4, 3, 2, 1. Okay, let's roll. Let's see where you are, okay? I hope that the force is strong with you on bond angles, because literally it's just memorization, and it's not like you're going to figure it out on the exam, so you got to know them or just figure out if you can figure out from the geometry itself. Alright, so bond angle is not a 180, like they try to fool you. They drew it as a 180, but then they said it's not. So your job is to figure out what kind of geometry is around this carbon. Well, what kind of geometry is it? Trigonal planar. It's a flat plane, okay? So 120, and your justification is either you mentioning the geometry of trigonal planar, and that would probably give you points, though it's not denoted here, or 2, mentioning there's just 3 electron domains in a plane to represent a 120-degree angle. So electron domains is a really easy way to mention or justify your bond angles. And then the next one, y is not 90, though it looks like it's a t or an x. So you know that that's a tetrahedral geometry. 1 and 9.5, 4 electron domains, or I'm noting that it's a tetrahedral arrangement. That might give you credit there, but I like the fact that we're mentioning domains here because it's an easy way to state your justification. So, sorry, you guys got 1 point for angle and justification, 1 point for angle and justification. And then, oh my goodness. Okay, so who feels like they did this right? Very few of us are confident ourselves. I love it. Okay. So it's nothing new. It's a carboxylic acid. Formic acid is a carboxylic acid. Not that you have to memorize that, but if you're just looking at a trigonal planar arrangement and you have 2 O's to bond, you know those H's are not going in the middle of anybody. They have got to be terminal, right? They've got to be in the ends. And so for carbon to achieve octet, you have to put a double bond on the carbon to oxygen bond. If not, you put the lone pairs on the carbon, and that is usually never right. So you got to plan for just the correct skeletal structure with your single, 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 and double bond, not the lone pairs. And you get one point for having 100% correct Lewis dot structure, which includes, of course, all the lone pairs in their appropriate locations. So it's a 2-point drawing. Yeah, I think that was a 4-point question. 4-point question. All right, moving on. Questions here? Questions here? I love it when you guys talk to me. I'm just overwhelmed with response. Okay, so this one, again, drawing, I heard a lot of you guys mention orientation. But just FYI, which of these is the lithium atom? The big one or the small one? Good. Cations are small. Added electrons making anions are larger. So that might help a little bit with your drawings. But really, you're identifying it, so you shouldn't have to do it based on size, but they sometimes do have you base it off size. So in order to get all your credit, your sketch had to include at least one lithium cation, one chloride anion, labeled and charged. So if you didn't put the charge, you don't get any credit because you didn't follow instructions. Draw at least, well, they have 4 water molecules, so you should put kind of symmetrically, like 2 and 2, 1 on each ion, with the oxygen oriented towards the oxygen is partially negative, so it should orient itself towards the lithium's cationic charge, and then the hydrogen end of water molecule should be oriented toward the chloride because of the opposites attract. So there's not actually a drawing here, but can you guys picture that? Yes. Yes, ma'am. I wouldn't draw charges on water unless you're putting a partial charge. It's very obvious partially charged. Like, oh, this marker is wonderful. If you put your lithium plus, and then who should orient itself towards lithium, guys? Oxygen. Like this. If you put like a partial negative like that and a partial positive like that, they wouldn't take off points at all. Like you get all your points. Okay. All right. Next, 2 L's, a 2-point question. 1 point for the correctly drawn particulate representation of water. That means like you know how to draw water. Let me tell you, people will be putting 2 O's and an H. It happens, and I hate it, but it's just stupidity. Okay, can't fix stupid. And then orientation of the water molecules correctly with the charge. I'm just saying, in honors chem, they keep doing it, and I'm trying to break it from them. It's like, it's hard. All right, we made it through most of this one. We're going now. If you did it, shame on you. Okay. Ethine, you guys know kind of your vocabulary with organic. Y and E does mean a triple bond, but if you didn't know it, and you had your structure or your formula, all you had to do is count your electrons up and draw it yourself. Okay. So if you didn't know the Y and E is a triple, you can at least figure it out from electron or valence electron counts. So triple bond, I think that's 1 point. Yeah, 1 point for your correct loose structure with a triple bond. And then shortest carbon bond, well, which one should it be, guys? Right, ethine, which is your triple bond. You got a point for the correct choice being ethine, which you just pull that directly from the chart itself. And then your justification is that triple bonds are shorter than single bonds. Don't say more. Who wrote more than that? Good, we're getting better. Not trying to blab on forever with our justifications, just simply because you're not going to have time. What is this one asking? Oh, okay, what was the geometry on C? That one right there. Okay, so we have 3 electron domains, right? So you're counting this, these 2 dots as a single bond, these 2 dots single bond, those 2 dots is still one entity, but it's a double bond. So we have 3 electron domains, which is going to give us trigonal planar, and then the other carbon over here, tetrahedral. You're going to notice this one is also, you also are allowed credit for saying distorted tetrahedral, simply because there's this like big honking ligand to the left, and then there's 3 little hydrogens to the right, so it's a little bit distorted in its bond angle, but you just put tetrahedral, you're still fine. So, but if you ever do see that terminology, it's just because of the unproportional or unsymmetrical nature of it. Okay, so is this true or false? 100% false. Like, you don't break bonds, right? Physical process. That would be a chemical process. So chemical processes will break bonds. We don't even say break IMF. Like, don't use the word break unless you mean it. So we want to say the words overcome IMFs. So 1 point for saying the statement is false with your justification. You can say boiling is a physical process, therefore the IMFs are overcome, not the intramolecular forces like the covalent bonds themselves. So that's a nice phrase. Overcomes intermolecular forces, but not intramolecular forces. 1 point. You guys doing okay? Okay. If you're looking at the table for the nonpolar creature, I think there were 2, the top and the bottom, so ethane and ethine. and that's because of their symmetry. You could also mention cancellation of dipoles overall would yield a nonpolar structure. Moving on. Okay, that was one point. And then, that's the last one. If you were looking for solubility between ethanol versus ethanethiol in water, ethanol has a nice OH group on the end, so it's able to do some hydrogen bonding with water, as well as like dipole, and even teeny bits of LDFs. But the strongest, of course, is your hydrogen bonding. And then the ethanethiol it has like a sulfur in it. Is that right? Okay. So it doesn't have the ability to hydrogen bond or make a significant attraction to water. But you could just say it's able to hydrogen bond. You did have to say something about the solvent interaction to indicate the solubility, or the nature of how solubility works, to get your full point there. Okay? Yeah. It's not that you need to know organic chem, it's that you need to be able to interpret how to draw organic structures, or interpret the IMFs they play with, or interpret, like, oh, that's a carboxylic acid, that's a weak acid. It's more the application of it. You don't have to like memorize organic at all. I would say alcohol groups, OH, carboxylic acid group, which is a C double bond O, and then H on the end, which make that the acidic portion. Those are the two most common functional groups that we work with in a reaction sense. But other than that, I mean, you notice they're telling you the stuff, you just have to apply it. Okay? All right, so you guys are moving here. Okay? Back in your group. So this is the next one, and then I'll tell you the next one in a second. There are still a lot of brownies. Saying. One electron domain. Yeah, I'll see you in a minute. I'll see you in a minute.
Unless they were all like N and then A. All vegetable bonds. So like a flat plane, like a linear structure, versus like a pyramidal structure, which is not the same plane. This is a 3D. It's basically 2D on a plane. 3D. Like 2D could be on a plane, flat, and 3D X, Y, and Z out of the same plane. No, it's X, Y, and Z. There's 3 planes in that.
Are you at 30 more seconds? Wishful thinking maybe, but still trying. I don't think you're done yet. Let me just give you another.
Oh, yes.
I would do bipolar. Also, followers that has
All right, we're gonna actually check it this time. Come back up to the front, guys in the back. If you didn't finish, you're still gonna learn. Still gonna learn. It's okay. Review. Alright, so we're on that 2011 one, and you probably noticed some of you guys were like, we just drew this. Well, that's okay. It's still good practice even if you see it twice in 2 minutes. So you have a structure. Basically, you're just identifying the hybridization. What's the first thing you start counting here? Electron domains. How many electron domains are there? 3. If you have 3 electron domains, you have a what hybridization? 2. S and then 2 P's, sp2. So the electron domains add up to the exponents of the hybridization label. 1 plus 2 is 3. That should be a, 5-second question. Next, you have a bond angle to describe. So if it's asking for the CX one, what's the geometry? I think that's the best way to approach it. What's the geometry first around the CX? Tetra, right? And if it's tetra, then you say the bond angle is 109.5. Okay, but your justification can be literally the geometry, or you can say 4 electron domains. All right, so you've got a reaction, blah, blah, blah. Draw the methanoic acid. What's nice is if you do feel comfortable with organic, oic acid should describe to you the functional group. It should describe to you C double bond O, OH. So 1, that's helpful, or 2, you can just draw it as a, looking at the electron, valence electrons, and making every have octet. So 1 point for correct structure there. With dots, if you don't put dots, you get no credit. I did see a couple with no dots on another structure. Okay, so this one, in years past, like recent years since this 2011 exam, which was this the exam I took? Hold up. No, never mind. I took 2010 exam. We used to get to choose our FRQs. No, 2007. Hold on, that was college. Never mind. 2006 exam. Yeah, we had to choose. We had like 9 FRQs and we had to pick 6, or we had 9, we had to pick 7. But you get more time to read them, right? And then you'd pick and choose, and you couldn't do part of it, and you'd scratch it out. It was not a good experience. Okay, so this one, and since then, they've stopped giving you credit for some parts of this, but I do want to show you from this particular exam, they give you multiple options. But the best answer for showing the water interaction would be with the strongest, where the strongest hydrogen bond would form. And it should be between the most polar regions of this methanol molecule, or methanoic acid molecule. So the OH here is going to be the part that's really primarily engaging with hydrogen bonding. So the O of water pointing towards the H would be a good way to draw that, or the H of this one pointing towards the O of the methanoic acid would be another option. So I think either one of those options would be great. They also gave credit because they said for one or a water molecule, so they also gave credit for that, but they don't always give credit for that anymore because it's not the best answer. Okay, so that's 1 point there with the orientation correct. Moving on. Yeah. Okay. Okay. So we've got this structure they provided us. We have to use this box to put our answer in, right, Cassie? We don't just make up our own stuff. Okay. So in the description of the answer keys, you'll notice everything's in dot form, but of course a line is totally appropriate. So everything is single bonded. Single bond between the N and H, single bond between the N and N, single bond between the H and N, and then of course the two hydrogens here. You have two lone pairs on those nitrogens. 1 point. 14 valence electrons if you were counting. And then this phrasing, I like to try to show you guys the odd phrasings and odd questions, because if I surprise you a lot this week, you will be surprised on Monday. A lot of you guys said, I like Gigi and I had a conversation about the weird FRQs as of last week, because they try to throw you things on the AP exam that you've never seen before. Not content, but like phrasing and questions and examples and scenarios, like the alloy with the gold ring, so that you're applying your knowledge in a new situation. So that's why I'm trying to give you some weird FRQs. But for this one, you're talking about being in basically a planar fashion or a non-planar fashion. If you have this geometry, what's the geometry around this nitrogen right here? Trigonal pyramidal. Trigonal pyramidal is a 3D structure, which is an XYZ plane kind of feature. That's what 3D means. But if it's a 2D structure, anything that's planar, linear, trigonal planar, square planar, that's it. Those are the only ones that would exist in a single plane. So this, of course, would be no, they do not exist in a single plane because of the trigonal pyramidal nature. 1 point there. Then we had boiling point comparisons. Anytime you're doing boiling point comparisons, you must be mentioning IMFs. So with the first structure, the polar, because of the lone pairs on the nitrogens, it leaves us with a polar structure. They're going to be able to experience London, dipole-dipole, and hydrogen bonding collectively, right? It's a summation of all those. And then the ethane is only simply nonpolar, just London's version. So that's 1 point, just mentioning the different IMFs. The second point came from the literal comparison, like saying this has a stronger accumulation of IMFs, which is going to require more energy, which is going to have a higher boiling point than the other one. That's an assumption I think a lot of us make. We're like, yeah, if we just state the IMFs, they know, duh, the first one's going to be stronger, but we have to literally state that, okay? No assumptions here. So it was a 2 point question. The second point came from the relative comparison. Part D, they told you to make it act as a base because they said pH had to be greater than 7. Literally, you just have to say, okay, bronze to bases. What do? They accept H pluses from the water. Water is amphoteric. It can act in both ways. So water donates its H plus here, makes N2H5 plus and an OH minus. Make sure you have your charges there. Because your explanation was not needed, your reaction was your explanation. Cool? Who got that? Just gonna be like thumbs up. Smart cookies. Okay. So, but that question it's not so easy. You're like, okay, I've never seen this reaction before. What do I do? You just have to think about being greater than pH 7. What potentially could that mean? Okay. Redox or acid base or decomp? Redox, right? Oxygen went from O2, which is a zero free element state, to what? To what? 2 minus, and then nitrogen went from +2, right? Or negative. Okay, so you had to make sure it was redox, right? One was oxidized, one was reduced. But it definitely went to a free element state. So in your justification, you would reference changes in oxidation state. 1 point is meaning it's the oxidation reduction. with your explanation, you can mention one gained electrons while the other lost. You can also mention the specific oxidation state changes and so forth. Entropy change, we went from liquid and 1 gas to 2 moles of gas. So if you have states of matter in your different states of matter in your reaction, that's usually what you go with in terms of looking for entropy changes. What's that, Drew? 3 moles of gas, thank you. So with that, you have a positive delta S because it's increasing in entropy, and there's a net increase of 2 moles of gas because of that change from 1 mole of gas to 3 moles of gas. And then that's going to show us the overall justification. And, oops, dang it. Last one, true or false, that statement in the box. Why false? What did they say? They said breaking bonds does what? Is exothermic. And show me why breaking bonds is not. All right, but in the exam, you wouldn't have a partner with this activity. You would just be like, okay, karate chop. Okay, that means breaks bonds. That means endothermic, right? Nope, don't say, okay, Ricky, break my bonds real fast, right? Don't talk to each other during the exam. They're in here like karate chopping each other. In love, what's going on? Oh, okay, so 1 point, and they mentioned both of the false statements, but I think the one most of us would see up front is like, hey, breaking bonds is not exo, it's definitely endo. And then overall, with that being very exothermic, you should have more energy released in the products forming than the energy taken in as the reactants are broken. I think that was 8 points. Not sure. 6, 7, 8 points. Or is that the last one you just did? Okay. Well, with 10 minutes left, I'll tell you there are 2 things. I got a lot of responses from you guys on like what you want to focus on this week, and it's like it's everything, and I can't do everything this week. Okay, we've been doing equilibrium, kinetics, thermo, lab stuff, electrochem, but I'm going to tell you, redox is going to be a battery or changing oxidation states. So you can begin to study your galvanic and electrolytic cells. The memorization side of that is really like positive E cell means spontaneous, galvanic, negative E cell, electrolytic, non-spontaneous, and then all those other variables that correlate. But I wanted to show you 2 exams that we're not going to get to take. If you just Google AP Chem for response 2016 or 2017, you can just look through those for maybe the next 10 minutes just to say, okay, yep, I can do that question, or oh gosh, this is a weird one, I'm not sure how to approach this, and look at that now. And of course, the scoring guides would have the question and the answers embedded. So those are just 2 really good ones since they're the most recent. So they model the question types. They model some similar concepts they like to keep asking questions on. And of course, your big idea 1. I'm not probably going to take these PowerPoints up until like the day after the AP exam. Because why would I take them up before? Right? So just if you have not made progress on 2, I'm suggesting you're working on 1. But we're about done. We're getting like cumulative review the rest of the week, okay? So take a couple minutes for yourself to figure out where you need a block in life. I suggest this first. Yes, give me 1 second, so let me pause this video.